total river flow observations. But you also see the result from subflow separation. This time it's only the base flow that is shown, the pink series. And you can see that the base flow is identified here as a fraction of the total flow. Now when we plot the same time series on a log scale, so the vertical scale is a log scale now, you see that during long dry periods the base flow is decreasing in a linear way. And this is because of the log scale. If we wouldn't apply the log scale, we would see that the base flow is decreasing in an exponential way. We call this behavior exponential recession. So the flow is decreasing in an exponential way. But because of the log scale, the exponential decrease becomes a linear decrease. Now the sloped lines, the green lines in this case, in the plot, they show the typical slope that the base flow follows during those dry periods. Now this exponential decrease during dry periods is not really coincidental. It happens for most of the rivers and river catchments in the world, and it's not only observable for base flow, you can also see that for interflow and overland as well, that they typically have exponential recessions. Now the exponential recession behavior, like we just discussed, like we most often observe for individual runoff subflows, because of this behavior, most often the routing of this kind of subflows in hydrological models or in rainfall runoff models is done by a linear reservoir model. Now a linear reservoir model is a model where we have inflows, we have outflows, and there is storage. The inflow might represent the rainfall falling on the catchment. The outflow might represent the outflow from the catchment runoff, for instance, and the storage might be the storage of water in the catchment. Now the outflow is assumed in a linear reservoir model linearly depending on the storage, so that's why we call this a linear reservoir model. And this is the equation that can be applied to simulate such a model. So at each time step, the outflow from the reservoir, Bt, at a certain time step t, is calculated based on the outflow from the previous time step, Bt minus 1, and based on the inflow, the Q, at the previous time step, t minus 1, and at the current time step, t. So we just take the average of the inflow during one time step from t minus 1 up to t. Now this reservoir model has one parameter, k, and k is called the reservoir constant. It's also called the recession constant. And the reason why we call it also recession constant is because the parameter k controls how slow the water will move out of the reservoir. So if k is small, the water will move out in a quick way. If k is large, the water will move out in a slow way. Now, obviously, when the inflow is higher than the outflow, the reservoir will fill up, and when the outflow is lower than inflow, the reservoir will empty. But when there is no inflow in the reservoir, so this means when we have a dry period, so there is no rainfall falling on the catchment, then the outflow will decrease in an exponential way, like most catchments behave. There are dry periods. For most of the catchments in the world, you see that catchment runoff is decreasing in an exponential way, and it's exactly the same property that we also have here in this linear reservoir model, and that's why this model is so often used for describing the routing of subflows in catchments. Now more specifically, the k parameter value can be seen as the time it takes for the catchment runoff to decrease from an initial flow value, for instance the peak flow we have after a rainstorm, to a reduced flow of exponential function of -1. And if you calculate its corresponding value, you come to the value of 0.37, that means 37%. So the k value is the time during which the initial flow value is reducing up to a fraction of 37% of the initial flow value. So that's another way of defining the k parameter value. Now the linear reservoir model, as we just explained, can in fact be seen as a low pass filter. This means that when a time series is used as input into the model, and any time series can be decomposed in different frequency components using, for instance, Fourier analysis. You know that a time series can have slow components, it can have quick components. But basically, the linear reservoir model, because it is a low pass filter, it will only pass the lower frequency components. So that means the slow components. The higher frequency components, they will be blocked. They are not passed by the model, by the filter. And that's why we can use a linear reservoir model for blocking the quicker flow components and passing the slower flow components. And that's why we call the linear reservoir model also a low pass filter. Now, if we make use of a linear reservoir model as a filter, and we put into the model a total flow, we send that to the linear reservoir model acting as a filter. What is coming out then is the slow flow component of that total flow. And what is blocked is the quick flow component. More specifically, if we make use of a linear reservoir model with a K value equal to the recession constant of base flow, you get as filter result the base flow. And what is left, what is blocked, what is the signal that is filtered out, isn't the quick flow. That means overland flow plus interflow, for instance. But of course, not all the total flow leads to base flow. And that's why we have to apply a reduction factor, which is called W in this slide. W is a value between 0 and 1. And the W value accounts for the fact that only a fraction of the total flow leads to base flow. In fact, 1 minus W is the fraction of the total flow that leads to base flow, and W is the fraction that leads to quick flow. And this leads then to those two equations for the filter. If we want to separate a total flow series, yt, in its slow and quick components, the slow component bt, the quick component ft, we just apply those two equations. The equations or the filter has two parameters, k and w. K, the recession constant, and we take the recession constant equal to the recession constant of the slow flow component that we aim as output for the filter. And the second parameter, w, is representing the fraction of the total flow that belongs to the quick flow. 1 minus w is then the fraction that belongs to the slow flow. But the question is now, how can we estimate those two filter parameters k and w? Well, the k value can be assessed by analyzing the slope of the flow during recession periods. And so when the flow is exponentially decreasing during dry periods. And as already discussed, when the flow is plotted on a log scale, during dry periods, the exponential recession is shown as a linear decrease. The slope of this linear decrease is nearly the same for all the recession periods in the time series, because the recession slope is mainly determined by catchment characteristics, such as the catchment area, the topography, the land use, the soil type, and so on. And that are all characteristics that do not largely change in time. Now you can expect that the k value is smaller for a smaller catchment, for instance. And the k value is also smaller for a catchment that is more steep, or that is more urbanized, or that has more sandy soils instead of clay soils. Just indicating that the k value indeed depends on this type of catchment characteristics. But now by means of sloped lines, like the green lines shown in this plot, you can try to assess in a visual way the mean recession slope. So the average recession slope when you look to all the dry periods in the time series. And this gives you an estimate of the k value based on a visual observation. Now, one disadvantage of the use of this log scale plot is that noise, which you often have on flow observation, very often if you do flow observations you have some noise, some measurement errors. Well, this noise, those measurement errors, they are enlarged by the log scale, especially for the lower flows. And that's what you see here in the plot, a lot of noise. But interestingly, this noise is also removed after you apply the filter. Why? Because indeed the quicker flow components are blocked by the filter. This is another example where there is less noise present in the flow observations. Again, you see that during long dry periods there is a linear recession, at least if you plot your flow on a log scale. And again, using lines, in this case the yellow lines, the slope lines, you can try to assess the mean slope during dry periods, and this gives you an assessment of the k parameter value. Next we come to the second parameter of the filter, which is the w parameter. And obviously what we aim for with our filter is that the base flow filter result is close to the real base flow. So that means that the base flow as a result of the filter should follow the total flow as close as possible during the base flow recession periods. Now, when the filter gives a base flow result that is too low, then the W parameter is too high, because the W parameter is indeed a fraction of the total flow that belongs to the quick flow. So if the base flow result is too low, it means that the W is too high. However, when the filter result is giving a base flow result that is quite okay during the base flow recession period, so that means a base flow result that follows the total flow quite closely during the base flow recession period, but if it also includes part of the quicker flow components, then the W parameter is too low, because the filter is not only giving you the base flow result, but also incorporates part of the quicker flow components. Now, if you look very carefully, although it needs some experience, you see that there is an inflection point where you can clearly separate the slope of the base flow recession from the steeper slope of the quicker flow components. And in fact, on the right side of this inflection point, the total flow should match the base flow, and on the left side of this inflection point, the total flow does not only consist of base flow, but it also consists of quicker flow components. So that's why the base flow filter result should follow the total flow quite nicely on the right side of the inflection point, but on the left side of the inflection point, because there is also quick flow on the left side, base flow filter result should give you a result lower than the total flow observation. This is another example where you can, where the inflection points are indicated. You see the base flow filter closely follows the total flow during long dry periods, always right of the inflection point, but left of the inflection points you see that the base flow filter results are lower than the observed total flows. Now, by doing trial and error, by visual inspection, as just explained, you can try to assess the K and the W parameter values, of course, based on experience as well. Now, note that there is in fact no need to have very precise estimates of the K and the W values. Rough estimates most often are sufficient, because you have to take into account that the filter is also a model, and a model is never producing perfect results. You always have some model inaccuracies, some uncertainties, and this means that in some periods you might see that the filter is giving systematic overestimations in comparison with what you assess as being the real values, and in other periods the filter might lead to systematic underestimations. And what you try to aim for is that on average, when you look to the full period, to the different long dry periods in your time series, that on average your filter is giving results which are as good as possible. So that means that, in other words, if you look to all the different periods of your time series, that you expect or you should have in 50% of the cases overestimations, and in 50% of the cases underestimations. But take into account that the filter is never perfect. It's in fact a model on itself. Now, so far we explained the base flow filter, but what about the interflow and the overland flow filter? Well, for doing the interflow filtering, you can apply the same filter as for the base flow, and basically what we do in practice is we apply 3 different steps. In the first step, we might need to account for the fact that in some rivers there is not only catchment rainfall runoff that is entering the river, but it can also be that the river is also receiving some water coming from some external sources in the catchment, like wastewater treatment plants or industrial emission flows. Now, because those external inflows do not show exponential recession behavior as catchment runoff does, the filter may not be used for filtering this type of external inflows. The solution for that is that we try to assess this type of external inflow in the river, and then we subtract this external inflow from the total catchment runoff or the total river flow, as observed, for instance, at a gauging station. So if we subtract from the total river flow the external inflow coming from external sources, that means non-rainfall runoff, what is left then is of course the pure catchment runoff. And this pure catchment runoff can then be used in a second step to apply the base flow filter to, in order to obtain a base flow filter result. What is then left is the quick flow, and then we apply the filter a second time in order to separate this quick flow in total flow, interflow, and in overland flow. Now, coming back to the first step, subtraction of